Okay, Ji, today we'll discuss graph reversal. In the last lecture, we discussed the graph theory and the concept of graph and the application where the graphs can be used. So today we'll discuss graph reversal or you can say graph searching algorithms. So there are basically uh, the idea overall. The idea is that given a graph G, or as we said in the last lecture, that we represent a graph using two sets, a set of vertices that is V and a set of edges that is E. So when we take these two sets, we call that we have represented a graph. So when we are given a graph that is either directed or undirected, it doesn't matter. The problem of graph reversal, if we just formulate the problem, the statement is that we want to explore the entire graph. Okay, so exploring the graph means that we want to go to every vertex of the graph and visit it. Okay, by visiting what we can do is that we can say that maybe we want to print the value, maybe we are running an algorithm of shortest path, or maybe we are running an algorithm to find these subgraphs that are connected. So for all these algorithms, what we need is that we need to systematically explore the graph. We cannot randomly or haphazardly go from one node to another and try to see if we have visited all the nodes or not. The only way we can do is that we explore the graph starting from a fixed point and then systematically try to search its neighbor on the basis of some rule, and then move on to the next neighbor or move to the neighbor of the neighbor. So there are two techniques. Okay, so the two techniques are breadth first and depth first search. Okay, so the breadth first is that, for example, this is a graph in which, if I represent it graphically, we have multiple vertices. So if I start from this fixed node, maybe starting node, I can say the vertex V. So if I start from this V1 node, for example, so for a breadth first, what I would do, if this node is connected to these two, and then further maybe this is connected to these two vertices, this vertex is only connected to, for example, this is the layout of the graph. So V2, V3, V4, and this is V5. So if this is the overall graph, then if I start from V1 in a breadth first search, what I would do is that I would like to visit these neighbors of V1 first, and then I can move to the next level of the neighbors. So that what you can say is that first I would try to process the nodes that are one step away from the starting node, and then I would actually add another step, and I would go to two steps away from the node. Then I would add another step, and I would say now I would go three steps away from the starting node. Okay, so visiting all the neighbors at one level and then moving on to the next level is the breadth first technique. I would explore these neighbors in the complete breadth of the graph, and then I would move to the depth. Okay, so that's breadth first search. And in depth first search, what I would do is that in a graph, for example, taking the same graph, what I would do is that maybe um, if I take the same graph, I would simply say that starting from V1, I would take either the left or the right, first or the second neighbor. And if I take the first neighbor, then I would further explore from this specific branch and maybe go to the first neighbor of V2, then maybe to the first neighbor of V3. So that would be exploring the entire branch until I find no other node on this branch, and then I would backtrack and move to the next branch, and then I would further backtrack and move to the further branches. So that would be going into the depth first, and then coming back and exploring the breadth of the graph. So these two techniques are mostly used. All the other algorithms are actually the variations of these two, either of these two searches. So if I'm running an algorithm to find the shortest path in a graph, then I would start from either the breadth first or the depth first search. So there are many algorithms that are based on these two searches. So let's see the breadth first search first. So the breadth first search, as I said, that I would like to explore all the neighbors at one level in a sequence, and then I would move on to the next level. So the overall idea is that we would use a queue in this algorithm. Okay, so the queue would be used to store all the neighbors in it, and then I would process that queue. So in that way, I would be processing the neighbors in a sequence. So the queue would maintain that sequence that I said that there should be a rule that in which sequence I would be visiting my neighbors. So that this rule is maintained by this queue. So the overall idea is that starting from an empty queue, I would just insert the starting node that is maybe v1 into the queue. Now that's the only node in the queue, and then I would go into a loop. And in this for loop, I would take out the front element from the queue and process all its neighbors. And the processing means that I would insert all those neighbors into the queue as well. So what it would do is that, for example, if this is the V1, in fact, I would go into the example in the next slide. Okay, so the idea is that I would keep repeating this process that I would take the front of the queue, mark it visited, and include all its neighbors into the queue. Okay, so the idea, this is the formal way. Create an empty queue, mark V, the starting node as visited, and put it into the queue. Now this is the only node in the queue. Then I would simply go into a generic loop. What it would do is that it would remove the head of the queue and mark and enqueue all the unvisited neighbors of the queue. So this unvisited neighbor, this is the important part here. How I would actually manage this is important in the implementation, because I need to check every time whenever I find a node that is adjacent to my given head of the queue. I would check if it's already processed or not. If it's already processed, then I would not reinsert it into the queue. I would not insert it into the queue again, because if it is processed, then it is already in the queue. Okay, so if it's already in the queue, then I would not insert it again. There should not be duplicates in the queue. So making sure that the node is marked and it is not reinserted or duplicated into the queue is important here. Okay, so let's see a dry run. So if I follow this algorithm, what I would do, what I would find at the end is that I would actually visit all the connected parts of the graph. And if there is an unconnected part, then it would be marked as unvisited. Okay, so if I have 6 vertices and after running all this complete algorithm, I still have one or two vertices that are unvisited so far. It means that the graph is not connected. So this algorithm uh, uh, can be run to check the connectivity of the graph as well, or connectedness of the graph as well. Okay, so if after running this algorithm I still have some unconnected or unvisited nodes, it means that those nodes are not connected with the initial part from where I started visiting the this graph. Okay, so let's run this algorithm on this graph. So what I would do is that initially I created a queue. This box represents a queue. So this is empty so far. So I created a queue. In the second step, I started from this node. Okay, so this node I marked it visited. So marking it visit, in this case, I inserted it into the queue. Okay, so these are the color captions that I have given. This brown node is actually the top of the queue. Okay, this brown color. So this S is now on the top of the queue. It's here in the queue. Okay. Whenever I would mark a node, I would color it blue. All those nodes that are not visited, they are still this color. These are black in color. And if a node is processed, it has visited all its neighbors as well. And once it got into the queue, it is now removed from the queue. It means that the node has finished its processing, and I would mark it green. Okay, so let's see. Starting from the queue, now I would go into the while loop. So in the while loop, what I would do is that I would um, um, dequeue this node from the queue, dequeue it, and then mark and enqueue all the unvisited neighbors. So all those black nodes that were neighbors of S. This is a directed graph. So neighbors are 2, 5, and 3. I mark them discovered. They are now newly discovered nodes. What I need to do them, I have marked them and then I need to include them into the queue. So I would insert them in the queue. So S would be removed and 2, 3, and 5 would be inserted. So 2, 3, and 5 are in the queue. The sequence doesn't matter here. This is the same sequence maybe in which sequence you have created these vertices while creating the graph. Maybe you read them from a data file. You maybe the user inserted them into the system. Maybe these are the messages that you received from the network. Maybe these are the friendship requests on Facebook in a sequence. They appear to you or they arrived you. So two was the first element, then three, and then five. So this is the sequence. It's not the sorted. It's not guaranteed that it should be sorted. Maybe in the neighbors list of this node S, 2 was the first neighbor, 3 was the second neighbor, and 5 was the third neighbor. It's not that the values are inserted in the sorted sequence. It's only that the edge list of this vertex, it contained 2 at the top, then 3, and then 5. So that is why I've inserted them in this sequence in the queue. Okay, now I've included all the nodes in the queue. This part is also done. Going back to the while loop, what I would do is that I would again remove head of the queue, that is node number 2. So I have removed this node number 2 from the queue. And after removing 2, I would mark and include all the unvisited neighbors. So the unvisited neighbors, or in fact, I would first see which are the neighbors. So neighbors of 2 are this black node and this node number 5. But this 5 number node is already discovered. So this blue color, actually, this should be a data structure. Remember, this should be a data structure here that makes sure that it contains all the nodes that are already discovered. So whenever I would go into this mark step, I would simply insert that new node into this data structure. Maybe this is a set. So I would insert that node in this set, and I would say all the nodes present in this set are the nodes that still need to be processed, but they are discovered. And this green one is again a set that says that this is again a set, and it says that all the nodes that are finished, that have been processed, are in this set. So either the node is in this set if it's processed, and if it's only discovered, then it would be in the second set, the blue set. Okay, so I can name them blue set and green set. So set is the data structure. Maybe you can use an array or maybe hashing function. Okay, whatever you use, but there should be a data structure that maintains the discovered nodes and the finished nodes. So these should be two different data sets, in fact. Okay, so then I found out that this 5 is already discovered, so I should only mark this black node as the discovered node. So this is node number 4. So for this node number 2, 5 is already discovered. I would not insert it again. Instead, I would only insert 4 in the queue. So removing 2 from the queue, 5 is already discovered. I only insert 4 in the queue. So you see 3 is now in the front, at the front of the queue. Again, going into the loop, I would extract or remove this 3 from the queue. 3 has these 2 neighbors, but 5 is already discovered. So I would only insert 6 into the queue. So 6 is in the queue. Now 5 is at the front of the queue. I would remove 5 from the queue and see the neighbor is only 6. This is a directed graph, so I would only go into the direction of the arrow. So only the 6th node is the node that needs to be visited. So I insert this 6 into the queue. Okay, so now, in fact, 6 was already in the queue, right? 3, after processing this 3, I inserted 6. So the neighbor of 5, that is 6, it should not be again inserted. So it's already discovered, it will not be queued. Instead, I would remove 5 from the queue, and now 4 is at the front. For processing 4, I would see the neighbors. Neighbors are 8 and 5. 5 is already processed. I would not insert 5 in the queue. Instead, I would insert 8 into the queue. So now 6 is at the front, and the neighbors of 6 are 7 and 9. Okay, so I would insert both these nodes 7 and 9 into the queue because these are newly discovered nodes. 7 and 9 in the queue. Now 8 is at the front. and 8 has no neighbors. Okay, so 8 has no neighbors because all the arrows are the incoming arrows. There is no outgoing arrow. So 8 is the node that is not connected to any other node. So I just process it. Then 7 is at the front. 7 is connected to the nodes that are already visited. 5, 4, and 8. So 7 would not insert anything into the queue. Then I would process 9 in all the nodes are already visited. So 9 would only, it is removed from the queue and it would not queue anything into the queue, which means that now the queue is empty and the algorithm finished. So the while loop terminates when the queue is empty. So after finishing the algorithm, what you see is that if I just mark the edges on the basis of which I discover the nodes, if you see this S was the starting node, this keeping this s as a root node, I can say that now all these connected nodes, they make a tree because this was the directed graph. S has three children in a tree. This 2 has a child 4, 4 has a child 8. So this makes a tree structure because I have removed all the redundant edges that were not used to visit this graph. So starting from node S, I can use all these edges to reach any node in the graph. So this actually makes a breadth first search tree. And in fact, this is the algorithm that we use when we try to find the shortest path or we try to find the minimum spanning tree. These are two more algorithms that we'll discuss in the next lecture. But this is the basis, this best first search is the basis of all both those algorithms. Okay, so at the end of this entire algorithm, I removed all the, or you can say I can remove all the redundant edges and pick only those edges that are required to connect the to keep the graph connected from the node S, starting from the node S. Okay, so if you are just wondering that how I actually kept the track of these edges that were used, it is the step when I in this while loop, when I mark the vertices, actually at that point I can actually I can also store the edge that was used to reach to this node. Okay, for example, from starting node to node number 2. So that was this line number 5 is the
सर
step from where I actually mark that edge. जी आकिब,
तो क्वेश्चन था कि क्यूज में वैल्यूज तो आ रही थी ना, तो रिमूव कैसे हो गई थी उसमें से?
मैंने ये देखें ये डीक्यू किया था. आई डिक्यूड दिस एलिमेंट फ्रॉम द क्यू. तो फ्रंट
तो
पे जो
सर
भी एलिमेंट है उसको मैं डीक्यू करता था और उसके बाद उसके नेबर्स को इंसर्ट करता था. ठीक है.
अच्छा अच्छा,
तो
ठीक है,
बेसिकली जो एलिमेंट प्रोसेस हो रहा था वो क्यू में से नहीं कर रहा था, लेकिन जैसे मैंने कहा कि उसको क्यू से निकाल के एक एक्स्ट्रा डाटा सेट हमने रखा हुआ था, हम उसमें डालते थे.
वो उसके अंदर जा रहा था, ठीक है।
हाँ, क्योंकि अगर हम ये डाटा सेट मेंटेन नहीं किए तो हम नोट्स को बार बार प्रोसेस करने लग जाएंगे. देखिए ना, इस एस के साथ तो कोई इनका भी एज नहीं था, लेकिन
अच्छा,
फॉर एग्जाम्पल ये जो नोड नंबर 5 था ये बहुत सेंट्रल नोड था, हर नोड से यहाँ पे एक एज आ रहा था, तो ये पता नहीं कितनी बार प्रोसेस हो जाता है
ठीक
ना.
है सर।
तो ये हम ये
ठीक,
जो रीप्रोसेसिंग थी ना कि हमारा एल्गोरिथम इनफाइनाइट लूप में ना चला जाए, वो इस ये जो मैंने ब्लू एंड ग्रीन कलर के डाटा सेट्स कहे थे ना, इसको आप सिंपल कहते हैं कि आपने एक सेट यूज करनी जो कि डुप्लीकेट्स को अलाउ नहीं कर रहा. तो आप सिर्फ उसके अंदर चेक करते हैं कि ये वाली वैल्यू ऑलरेडी अवेलेबल है, वो ट्रू या फॉल्स रिटर्न करता है. अगर वो ट्रू रिटर्न करता है तो आप सिंपली वहां पे नोड को इंसर्ट नहीं करते, आप कहते हैं ये डिस्कवर्ड नोड है या ये फिनिश नोड है. अगर वो फॉल्स रिटर्न करता है, ये दोनों सेट्स फॉल्स रिटर्न करते हैं, इट मीन्स कि ये अनडिस्कवर्ड ब्लैक नोड है. ठीक है, तो यहाँ पे तो कलर्स थे ना, लेकिन कलर्स को असल में हमने डाटा स्ट्रक्चर से ही मेंटेन किया हुआ था. ठीक हो गया.
ठीक हो गया।
चलिए आगे चलते हैं. So that was search, and I already said that the algorithm actually moves from distance k to distance k plus one in a systematic way, and discover the nodes at a further away distance from the starting node. Okay, so that was the overall algorithm, and this algorithm is the basis of many other algorithms. So we'll see it in a few more algorithms as well. Okay, so now moving on to the depth first search, that's in fact more simpler than the depth first search. you can say this is a recursive algorithm, or it can use a stack as well. Remember that recursive algorithms, they use a stack. In programming languages, what we said was that was the function called stack. So we can make use of that function called stack, or what we can do is that we can create a stack object for our algorithm as well. Okay. So what the algorithm does is that, starting from maybe from this node number A, this example is actually, it looks like a tree, but it is a graph as well, because the trees are the subset of a graph. So if I take it as a graph, I start from node number A, that looks like a root, looks like the root of the tree. So what I would do is that I would process its one child, and then instead of going to the next child, I would move further away from this starting node and move to the first child of the child of root. And if there is no more child of further children of this node number D, then I would go back, and for node number B, I would visit its second child, and then if it has a third child, and so on. Okay, so the logic is that I actually go in this way. I go to the extreme length of the branch, then I backtrack, I go to the previous node and move to the next branch. Okay, then in the next branch I go to the extreme left, maybe to the leaf node, and then I move back to the parent and move to the second child, and then move to the parent and go to the second child. And if I keep running this algorithm from N, I would again go back to this E, and then go to this node number I, then O. From O, this is the leaf node, I would move back to the I, then P, then move back to I, E, B, A, and then I would go into the right side of node number A. So that this algorithm actually goes towards the length of the branches, and upon finding a leaf node on the branch, it backtracks to the parent and then moves to the next branch. So that's simply like calling a function. I call a function A, it called the function B called function D. Function D terminates, it moves back to function B calls another function E. So that's just like a function call, and the function call is maybe the recursive functions. Okay, so that's the way in which a depth first search works. So the output of this specific graph would be um, D. D is the first node that is processed. I move from A to B to D. So D is the first node. Then I move back to this node and went to this. Uh, or maybe in other sense, what I can say is that if I just uh, redraw this, starting from node number A, if I just keep printing the nodes, then I would print A first, then I would print B, A, B, D, then E, H, L, M, N, I, O, P, and then C, F, G, J, K, and Q. So that's the sequence that's written here. Okay. So I moved onto the branches, and I kept moving downwards, going to the depth of the tree, and reached the leaf node, and then I backtracked one step before the leaf node, and then took the second branch, and so on. So that's the way this depth first search algorithm works. Okay. So the overall algorithm is that, um, what I do is that I just create a stack. I put this starting node number V, into the stack. So that's the top of the stack. Okay. And that's the only node on top of the stack. Then I would pop it from the stack. In fact, it's not the popping from the stack, it's just peeking at the top of the stack. So this is the stack, for example, and this node V is the only node in the stack. I would just see that this is the node V in the stack at the top. Then I would simply read the neighbors of this node V. So I would peek the node. I would not remove this V. This V would stay there in the stack. I would simply peek, and I would see the neighbors. If it has any unvisited neighbors, I would push those neighbors onto the stack. So those neighbors would come on top of this node. So after putting the neighbor on the stack, what I would do is that, in fact, instead of putting all the neighbors at once, I would just pick one unvisited neighbor. If it's unvisited, I would mark it visited and push it onto the stack and move back to the while loop. So the idea would be that if I had this V on the stack, I would simply see which is the first unvisited neighbor of V. Maybe that is node number U. I push that U onto the stack, and then I would again peek on top of the stack. That is node number U, and I would visit this first unvisited neighbor of U. Maybe that is W onto the stack, and then I would again peek on top of the stack, and I would pick this W, and I would insert the first maybe unvisited neighbor of this W on top of the stack. So this is the way a function call works. Similarly, this depth first search behaves the same way. Okay, so that's the algorithm how it would work. So let's run this algorithm on this specific graph. Taking this maybe this is the adjacency list. It shows that it has A, B, C, D, E, F, G. It has these seven vertices. This is the set of vertices, and this A has these four neighbors, B has one neighbor, C has one neighbor, D has two neighbors, and so on. So this is the adjacency list. Okay, this is a list. This is the way we stored this graph into the computer. So starting from the first node, maybe A is the first node, we start from this node. So we mark it the active or the current node. And the algorithm said that we would actually see the neighbors of the first neighbor of this node A. So the first neighbor is this node number F. Okay, so if this is the stack, this node number A had all these edges: A to F, A to C, A to B, and A to G. These four tuples, these are the entries for the edges. So I would pick the first edge. This is A of A to F. Or I can see from this adjacency list as well that F is the first neighbor of A. So I would pick this F that is unvisited and push that onto the stack. So that was the algorithm. I discovered this F, I push that F onto the stack. Now F has these A, E, and D three neighbors, or you can see FA, FE, and FD. These are the three edges. So I would pick this first edge here, and this is the node A. Node A was already visited. Remember, it's already marked. So I would not push that A onto the stack. Instead, I would go onto the second node, second edge. That is FE. So FE would be the newly discovered node. I would push that E node onto the stack. Okay. Now for this E, if you see the adjacency list, GFD, or you see this edge tuples here, G is the first unvisited neighbor. So G is unvisited. So I would discover this G and push that G onto the stack. Okay, so G has E as the first neighbor, E is already marked, and second neighbor is A. So A and E both are already marked. So G would not insert anything onto the stack. Instead, it would process itself and just remove this specific stack element from the top. So E is already marked, A is already marked. So G would not insert anything. Okay, or if I just go back to the algorithm, I did not discuss this else. In this else part, this else part is the statement when there is no unvisited neighbor of the current node. Okay, so this G has no unvisited neighbor. I would not go into the if. I would go into the else, and I would need to pop this specific node from top of this. Okay, so in this else, I removed this G, which has no undiscovered no neighbor. So I remove this G from the stack. Now I move back to E. I process this G. Now I need to process this F. Okay, for this E node, I process this first neighbor G. It has inserted nothing on the stack, and then I move to the next edge that is towards F. F is already discovered, so I would not insert anything. I would move on to the next edge. Next edge is D. D is also discovered. D is the newly discovered node. Okay, D is the newly discovered node, so I insert D or push D onto the stack. Now this node D has two neighbors, F and E. F is already discovered, E is already discovered. Okay, so D would not insert anything, and in the third iteration, This D has no unvisited neighbor, so it would I would pop that D from the stack. Okay, so now again E is on top of the stack and E has no edge left that is unprocessed. So I processed G, I processed F, I processed D. So E has no unvisited neighbor. Again, for this E, I would go into the else part of the while loop, okay, and then I would pop this E from the stack as well. Now coming back to this F, just like a function call, this F made the function call for A, it resolved without doing anything. For E, it did so many steps, then E was removed from the stack. Now for this F, I need to visit this D. D is already finished, already processed. So D is already processed, it means F has no unvisited neighbor. So I would pop this F from the stack as well. Okay, so you see, I started from A, I moved to this branch F. From F, I moved to E. From E, I moved to G. So now this G had no unvisited neighbor, so I moved back to E. I discovered this D as well. This was the second branch. Then I moved back to E. D had no neighbors, so I moved back to E. This was the backtracking. And for E, there was no unvisited neighbor. I dropped this from the stack as well and moved a step further back. I came to F. F had no unvisited neighbor. I further backtracked and reached the starting node A. Now I would go to the second branch of A. The first branch was F, this branch. Now for this node A, I need to visit the second. So for this node A, I visited this F, the complete branch. Now I need to move to this second branch C. Okay, so for this A, I visited this edge and marked C as the active node and pushed that onto the stack. C has only one edge that still goes to A because this is an undirected graph. So A is already marked. So C would not push anything onto the stack and it would simply be removed from the stack. So I removed C from the stack. Okay, moving back again, backtrack to A. A is on top. C is processed. F is processed. Now I go to the third edge, that is B. A to B. So this is the B node. This is a newly discovered node. I make this node active and push it onto the stack. B has only one edge that goes to the A, so it means A is already discovered and B would not do anything. So I would simply pop this B from the stack. Now for A, this A has the last edge towards G, but G was already marked from this path from F to E to G. So I would not process it again. In fact, this G would not do anything, and now I have no unvisited neighbor of A. So I will pop A again. So that's the end of the this algorithm. Then the stack is empty and the while loop is terminated. So once again, for this specific graph, what you can say is that, in fact, I can say that this edge was redundant. Only this edge was redundant. If I remove this edge from this entire graph, it would be but I can say, and in fact, this is not the only edge, and this edge as well, because these were the edges that were not processed. So if I remove only these two edges, then this graph becomes a tree rooted at node number A. So these two edges that did nothing into this algorithm. In this algorithm, these are two redundant edges in the graph. So I can actually use these algorithms to find the redundant edges from the graph, and if I remove those edges, the graph still remains connected. Okay, so for the depth first search and the breadth first search, both the algorithms actually also point out the redundant edges in the graph. And those were the edges that made them the graph. Otherwise, it could have been a tree. So removing those edges from the graph would make this graph into or convert this graph into a tree. Because the definition of a tree is that a tree is a structure that starts from a specific node that is called a root. And from that root node, there is only one unique path to reach any other node. So that's the definition of a tree. So if I remove the redundant edges from a graph, the graph becomes a tree. Okay, so that's the end of depth first search. Now let's just conclude this session and see what's the benefits of using these graphs. So these two algorithms. So Just take an example. Both these actually techniques are very useful techniques. We can use either one of them, but for some scenarios, one is better than the other. So for example, in this scenario, if we want to search, you have a family tree, for example, at your disposal, and you want to search your cousins or your siblings into that tree. So the family tree actually starts from the first parent of your family. So you might be on the leaf level of that tree. And if you want to search your siblings, it means that you actually want to search maybe the same level on which you are residing. Okay. But in order to reach that level, maybe it is maybe hundreds of steps away from the root node or from the starting node. So it means that if you take the breadth first search, because your siblings and your cousins will be on the same level, and breadth first search actually considers that you would explore the breadth, the same level, in one go, and then you would move on to the next level. So for the breadth first search, the problem would be that you have to explore so many nodes before reaching your level. And once you reach your level, you would explore your siblings maybe in a few steps. So breadth first search has its limitations. For the depth first search, maybe uh, the family tree is built where the lineage on which you are residing is towards extreme, maybe the right of the tree starting at your grandparent. In that case, you would have to explore all the tree that is on the left of your node. So both these algorithms, maybe for this specific application, would explore the entire tree or entire graph before reaching you, the node that represents you, and then maybe finding your siblings and cousins would start from there. Okay, so both these algorithms take their time, so they are similarly almost the similar algorithms. They would not actually make any difference if you use either breadth first search or a depth first search. But for some algorithms, depth first search maybe performs better, but for others, depth first search maybe a better choice. But the worst case is that they need to visit all the nodes. Okay, so that's the worst case. And then for that's the worst case in which you need to visit all the nodes before finding your solution or before finding the nodes that you want to search. Okay, and for some further application, as I said, that what you can see is that you can find the connectedness of the graph, because if after running the algorithm there are still some unvisited nodes in the graph, it means that those specific nodes were not connected into the graph, starting from node number s maybe. Okay, so you can check the connectedness of a graph. Um, then you can. I would actually come back to this point again, and I would ask you guys if you are okay. I would ask you guys to maybe comment on this, Kashif and Akib. I would ask you guys, okay? So just come up with some application uh, of this first point. Okay, how I can use this connectedness. Okay, the second point is I can construct a BFS or DFS tree from this graph. So it means that I can actually remove the redundant edges from the graph. That's very important as well. It has many applications. I would ask the applications of the first point from you, and I can explain the application of this second point. So when I remove the redundant edges from a graph, what I can achieve is that, for example, I have a graph of the cities of a country, and I have this uh, idea of connecting all these cities with each other. Okay, maybe I can do it like this. Okay, so this is the that all the cities are directly connected to each other, but it's too costly, because if I have, for example, I can reach node number from this node number A, I can reach this node number B directly, and from node number B, I can go to this node number C. Why would I need this specific road here? So in that case, if I want to reduce the cost of this connectivity, because constructing a road between two cities is a big cost, so I would actually not construct this node. Instead, I would reuse this already created road, and I would say, or I would direct all the people to, if they want to go to C from A, they should first visit B and then go to C. And that's a practical application. You would see in the maybe the map of Pakistan that not all the cities are connected directly to each other. You need to maybe take a longer turn, but you, in that case, you save some cost. Okay, so you reach a city, a bigger city that is closer to the smaller city maybe, and from that bigger city you take another road to reach that smaller city. But in this way, you only built this small road to connect A to C, and that reduce your cost. Using this specific only one edge, you connected basically two parts of the country with each other. You connected A with the C and you connected B with the C. Okay, so that's the application of constructing a BFS or DFS tree from a forest, from a graph. Okay, so finding out the redundant choices, removing those redundant choices from your decision making would actually give you a straightforward, maybe of less cost or economical solution. Okay, for the third algorithm, for this third path, determine the path length from one vertex to all others. So when I was actually connecting these edges to make this graph connected, I can actually check the cost of this. Maybe the cost is C1, maybe 10 miles or 10 kilometers. This is 5 kilometers. So I can actually count this cost as well. So counting the cost may give me the solution to the problem that if I want to find the best path to reach a destination. So maybe I could reach this node number maybe D as well, and D is also connected to B. So from A, I can go to D, D to B, and B to C. That is another path or another way to reach to C from A. So should I use this path or should I use A to B and C? So that would be actually dependent on the cost of these edges. So I would actually pick one of one of the two choices, and the choice would be the best choice that I can make, maybe the smallest distance. Okay, so the shortest path algorithms are dependent on this third point. Okay, so now coming back to you guys, Kashif, क्या बता सकते हैं कि पहले पॉइंट की क्या इंपॉर्टेंस है, डिटरमिनिंग कनेक्टेडनेस एंड फाइंडिंग कनेक्टेड सब ग्राफ्स, इसकी कोई एप्लीकेशन बता सकते हैं आप?
सर कनेक्टेडनेस से क्या मुराद है कि नोड्स आपस में कनेक्टेड किस तरह क्यों है?
कनेक्टेडनेस का मतलब ये नहीं है कि एक नोड से दूसरे नोड पे डायरेक्ट एज जा रहे हैं। कनेक्टेडनेस का मतलब ये है कि जैसे मैंने बताया था कि एक से सी, अगर मैं ये वाला जो जिसको क्रॉस किया हुआ है, मैं इस एज को निकाल भी दूं ना, तो ए से सी पे जाया जा सकता है। आई कैन मूव टू बी एंड देन आई मूव टू सी, सो सी इज स्टिल कनेक्टेड टू ए। ठीक है, तो इसका मतलब ये है कि किसी भी वर्टेक्स से मैं किसी भी दूसरे वर्टेक्स पे जा सकता हूँ। अगर ऐसा हो तो कनेक्टेडनेस होती है, अगर ऐसा ना हो तो कनेक्टेडनेस नहीं होती, डिसकनेक्टेड होता है। तो अगर मुझे ये पता चले तो इसका फायदा क्या है?
सर फाइंड कर सकते हैं कि एक सर, क्योंकि मैंने लेक्चर्स कम लिए हैं तो सॉरी, पर मैं कह ही सकता हूँ बिकॉज वी कैन फाइंड द सब ग्राफ कि मैं ए से फिर बी से फिर डी भी जा सकता हूँ। ये एक मल्टीपल चॉइस मिल जाती है हम लोगों को ना, कि हम मूव कर सकते हैं फ्रॉम वन पाथ टू अनदर पाथ, हम चॉइस मेकिंग कर सकते हैं।
थोड़ा सा और सोचिए। मैंने आपको इसलिए कहा है कि ये एप्लीकेशन मैंने स्पेसिफिकली तो नहीं अभी मतलब आपके साथ डिस्कस की ना, तो आप खुद सोच के बताएं कि अगर मुझे ये पता चल जाए कोई एक स्पेसिफिक, चलिए मैं आपको एग्जांपल देता हूँ। फॉर एग्जांपल मैं ग्राफ बता देता हूँ, फिर उसके ऊपर सोचिए आप। फॉर एग्जांपल जो ग्राफ है मेरे पास वो है कि आपकी क्लास के अंदर जो स्टूडेंट्स हैं, फॉर एग्जांपल अच्छा चलिए एक और एग्जांपल देता हूँ, एग्जांपल आपको ज़्यादा इंटरेस्ट देगी। एग्जाम्पल ये है, अब ये बहुत इंटरेस्टिंग सी बच जाएगी कि आपकी असाइनमेंट सबमिट हुई सारी की सारी। मे बी मैंने आपको जब पीएफ भी पढ़ाया था और मैंने आपको ऊप भी पढ़ाया था, तो मैं डीएस पढ़ा रहा हूँ, तो मैंने आपकी पुरानी सारी असाइनमेंट्स उठा ली, मैंने आपकी पीएफ की असाइनमेंट भी उठा ली, मैंने आपकी ऊप की असाइनमेंट्स भी उठा ली, और मैंने हर स्टूडेंट को एक वर्टेक्स बना लिया और उसके बाद मैंने स्टूडेंट्स की असाइनमेंट्स के कोड की सिमिलैरिटी को ना, कहीं से मैंने देखा कि ए और बी की दो स्टूडेंट्स हैं, इनकी असाइनमेंट में 5% सिमिलैरिटी है, तो मैंने उनके बीच में कैच लगा दिया और उस पर कॉस्ट लिख दी 5। उसके बाद मैंने बी देखा तो ए और डी की असाइनमेंट भी थोड़ी सी सिमिलर थी, तो मैंने उनके बीच में सिमिलैरिटी का एक एच लगा दिया। तो मैंने सारी असाइनमेंट्स के इस तरह से ना अपने ग्राफ में एडिशंस करता रहा कि अच्छा, अगर दो असाइनमेंट सिमिलर है तो मैं कोई कॉस्ट को मजीद किसी चीज से मे बी कॉमा लगा के दो वैल्यूज लिख देता हूँ कि असाइनमेंट 1 में 5%, असाइनमेंट 2 में 2%, इस तरह से सो ऑन ना। ठीक हो गया? ये बात समझ नहीं दोनों जरा, आकिब आप भी और काशिफ आप भी।
यस सर।
आपको नजर आ रहा है कि क्या इन्फॉर्मेशन मेरे पास आने लगी है? अगर मैं ये ग्राफ सिर्फ इतना सा बना लूं कि किस किस बच्चे की असाइनमेंट किस किस बच्चे के साथ कितनी सिमिलर थी, अब मैंने इसका ग्राफ बना लिया, बच्चे जो हैं, स्टूडेंट्स जो हैं, दोज आर दी वर्टिसेस, और जो असाइनमेंट की सिमिलरिटी की वैल्यू आई है ना जिस बच्चे के साथ, उस उन दो बच्चों के बीच में मैंने एज लगा के जो सिमिलरिटी की वैल्यू थी वो मैंने कॉस्ट पे लिख दी, एज की कॉस्ट पे लिख दी। ठीक हो गया? तो मेरे पास कुछ ये ग्राफ बन गया। अब ये ग्राफ आपके पास मौजूद है, ठीक है जी? ठीक है। तो ये जो ग्राफ है, इस ग्राफ पे अब ये कनेक्टिवनेस वाला जो है ना, आप जरा इसको सोचें कि कनेक्टिवनेस अगर मुझे पता चले किसी पार्ट की तो उसका मतलब क्या है। मैं जरा कॉल सुन लूँ, आप जरा इतनी देर सोचें। जी, कुछ पहुंचे काशिफ?
नो सर, आई थिंक नहीं सर, नहीं पहुंच सका मैं सर।
यार
लाइक
काशिफ,
डाटा।
एक ग्राफ बन गया है जिसके अंदर सारे बच्चों की असाइनमेंट्स की, मैं बेसिकली शायद हिंट दे रहा हूँ कि मैं प्लेजरिज्म के रिलेटेड कोई चीज बनाना चाह रहा हूँ।
यस सर, वो पता चल गया था प्लेजरिज्म।
पता चल गया? हाँ, तो वो बच्चे जो एक कनेक्टेड पार्ट का हिस्सा हैं, उनकी असाइनमेंट्स एक दूसरे से मिलती जुलती हैं। तो मे भी मुझे नई असाइनमेंट में सिर्फ उनको आपस में प्लेजरिज्म चेक कर लेना चाहिए, पॉसिबल यूनियन का ये मिलेगा, उनका किसी और के साथ मिलने के चांसेस कम है। ठीक है? तो मैं कोई ऐसा नेटवर्क बना रहा हूँ, मैं इसमें ये भी कह सकता हूँ कि दिस इज द कनेक्टेड पार्ट जो कि बहुत इशू क्रिएट कर रहा है। जो डिसकनेक्टेड पार्ट्स हैं, जो नोट स्पेशली किसी से कनेक्टेड नहीं है, वो तो बहुत ही वो बच्चे हैं जिन्होंने सारा अपना काम किया है, लेकिन मैं यहाँ से सिमिलैरिटी के पार्ट्स उठा सकता हूँ। ठीक हो गया? अच्छा, ये एक एग्जांपल थी। दूसरी एग्जांपल डिस्कस करते हैं, इसी की दूसरी एग्जांपल। अब इसका आइडिया थोड़ा सा चेंज करते हैं कि मैं ग्राफ किस चीज़ का बना रहा हूँ। पहला ग्राफ मैंने बनाया था इस चीज़ का कि मैं बच्चों की असाइनमेंट्स की सिमिलैरिटी की बेस पे ग्राफ बना रहा हूँ। अब मैं इसका दूसरा एग्जांपल लेता हूँ। दूसरी एग्जांपल ये है कि फॉर एग्जांपल मैं यूनिवर्सिटी में हूँ, यूनिवर्सिटी में फॉर एग्जांपल मैं ये देखना चाह रहा हूँ कि मैंने ना कोई अनाउंसमेंट करनी है ना। अब आजकल के दिनों में स्टूडेंट्स यूनिवर्सिटी में भी नहीं आ रहे ना। ठीक है? और मैं ये चाह रहा हूँ कि मैं कोई बात पूरी यूनिवर्सिटी को बताना चाहता हूँ, लेकिन मेरे पास कोई ग्लोबल ऐसी लिस्ट नहीं है कि जिसपे मैं ब्रॉडकास्ट कर दूँ मैसेज। ठीक है जी? तो मेरे पास ब्रॉडकास्ट करने
यस
की कोई
सर।
लिस्ट मौजूद नहीं है। और मैं ये चाह रहा हूँ कि मेरे सारे स्टूडेंट्स को मेरी बात पता भी चल जाए किस तरीके से, मे बी मेरे स्टूडेंट्स को भी, मे बी पूरी यूनिवर्सिटी में सारे बैचेस को। आपका तो थर्ड सेमेस्टर है ना फॉर एग्जांपल, लेकिन मैं ये चाह रहा हूँ कि मे बी फिफ्थ सेमेस्टर वालों को पता चल जाए, और सेवंथ सेमेस्टर वालों को भी, और फर्स्ट सेमेस्टर वालों को भी। ठीक हो गया? तो मैं उस केस में क्या करूँ, मैं फॉर एग्जांपल यूनिवर्सिटी के अगर सारे स्टूडेंट्स का डाटा मेरे पास मौजूद है, कोई फेसबुक का सोशल नेटवर्क का डाटा, तो मैं वहां से वो ग्राफ उसको उठाऊं और उसका ग्राफ बना लूं कि किस किस स्टूडेंट के कौन कौन से फ्रेंड्स हैं। ठीक हो गया? और मैं उसके बाद कनेक्टिवनेस चेक करनी शुरू करूँ हर स्टूडेंट की। और मुझे पता चले कि कोई स्टूडेंट 10 लोगों से कनेक्टेड है, कोई स्टूडेंट 15 लोगों से कनेक्टेड है, कोई स्टूडेंट 30 लोगों से कनेक्टेड है। और मैंने अगर कोई बात सब तक पहुंचानी है तो मैं फिर किसको कांटेक्ट करूंगा? किसको बताना चाहूंगा कि यार सबको बता देना आगे?
जिसके सबसे ज्यादा कनेक्टेडनेस होगी, जिसके सबसे ज्यादा अजीज होगी, जैसे लेंथ होगी।
ठीक हो गया। या तीसरी एप्लीकेशन ये भी कह सकते हैं कि फॉर एग्जांपल मेरे पास कोई फ्लाइट ऑपरेशंस है और मैं ये चाह रहा हूँ कि मेरी जो मे बी एयरलाइन है, मेरी एयरलाइन एक नया एक सिटी को कनेक्ट करना चाह रही है सारी दुनिया से। नया बिल्कुल हमने एयरपोर्ट बनाया है, नया एयरपोर्ट हमारे सिस्टम में एंटर हुआ है कि हम इस पे भी अपनी फ्लाइट लेके जा सकते हैं। ठीक हो गया। तो मैं कौन से सिटी से इसको कनेक्ट करूं कि ये सारी दुनिया से एकदम से कनेक्ट? ऐसा हो सकता था कि मैं कहता हूँ जी कि मैं फॉर एग्जांपल पाकिस्तान में कराची में भी लैंड कर सकता हूँ, सिटी में भी किसी ऐसी जगह पे जहाँ पे पहले पीआईए की फ्लाइट नहीं जाती फॉर एग्जाम्पल। तो मैं कहता हूँ अच्छा मैं वहां से कराची को कनेक्ट करता हूँ। फिर मैं कहता हूँ नहीं, कराची कनेक्ट करने पे तो कराची से आगे 10 जगह पे फ्लाइट जाती है। मैं लाहौर को कनेक्ट करता हूँ, अच्छा लाहौर से वो लाहौर से 10 जगह पे भी नहीं जाती, वहां से तो 7 जगह पे फ्लाइट जाती है। इस्लामाबाद से तो सिर्फ 3-4 जगह पे फ्लाइट जाती है डिफरेंट कंट्रीज पे फॉर एग्जाम्पल मैं कह रहा हूँ रफली ना। तो फिर मैं कहता हूँ अच्छा नहीं, अब इसको मैंने पीआईए के नेटवर्क में तो लाना है, लेकिन मैं क्यों ना इसको किसी ऐसे सिटी से कनेक्ट कर दूं जहां से सब ज्यादा फ्लाइट दुनिया में जाती है। मे बी मैं पाकिस्तान से बाहर किसी और कंट्री को, किसी और सिटी को पिक कर लूं जहां से मुझे पता हो कि शायद यहाँ से बाकी सारी दुनिया को फ्लाइट जा सकती है। अगर मैं पीए की फ्लाइट इस स्पेसिफिक न्यू सिटी से वो पुराने सिटी जिसपे बहुत ज्यादा फ्लाइट्स पहले आती थी वहां पे कनेक्ट कर दूं, तो यहाँ के पैसेंजर सबसे ज्यादा फायदा उठाएंगे। वो डायरेक्टली मेरी फ्लाइट पकड़ेंगे, उस बड़े सिटी में आएंगे, वहां से फ्लाइट पकड़ेंगे, दुनिया के किसी भी कोने में जा सकते। गॉट द पॉइंट कि कनेक्टेडनेस ऑफ द बिगर सिटी वुड बी बेटर। ठीक हो गया काशिफ?
यस सर।
चलिए जी, तो दैट्स वेयर वी स्टॉप टुडे। ठीक है, और ये डिस्कशंस दो एप्लीकेशन में डिस्कस कर ली ग्राफ की। अब हमारा ग्राफ पे एक लेक्चर रह गया है और एक या दो लेक्चर हमारे बी ट्री पे रह गए जो कि नेक्स्ट वीक में इंशाल्लाह हो जाएंगे। ये तो वैसे लेक्चर छोटा था, ये तो घंटे का भी नहीं हुआ था, 40 कुछ मिनट्स का था। तो मे बी मैं एक और रिकॉर्डिंग जो कि ग्राफ की आखिरी एप्लीकेशन एक रह गई है, वो छोटा सा एल्गोरिथम है, वो एल्गोरिथम मैं 15-20 मिनट का एल्गोरिथम वो भी अपलोड कर दूंगा, तो वो भी इसी लेक्चर का पार्ट हो जाएगा। ठीक है काशिफ?
यस सर।
ठीक है, और तो जो नेक्स्ट वीक के दो लेक्चर उनमें मैं बी ट्री डिस्कस करूंगा। ठीक है जी, कोई क्वेश्चन है तो पूछ सकते हैं।
सर कुछ क्वेश्चंस कुछ प्रोजेक्ट्स के रेलेवेंट आता है, क्या वो पूछ सकते हैं?
प्रोजेक्ट के रिलेवेंट मैं ख्याल है आज एक सेशन। ठीक है, चलिए मैं रिकॉर्डिंग स्टॉप करता हूँ फिर उसके बाद डिस्कशन करते हैं।